Good morning. My name is Sharon, and I am from CSE AIML from Section C. So today my topic is filter matrices. Filter matrices, a new approach to data analysis. So filter matrices can refer to several different concepts depending on the field, including the applications of a convocation filter, a small matrix, to an image to produce a new one. The use of a matrix to filter data in collaborative filtering systems or filtering gene barcode matrices in genomics to remove background noise. It can also mean a matrix that has elements filtered out based on specific criteria, such as in a data analysis or a statistical context, unlocking deeper insights by intelligently simplifying complex datasets. What are matrices and why do we need them? So the definition of matrices is that a matrix is a rectangular array of numbers, symbols, or expressions arranged in rows and columns. They are fundamental structures for organizing complex data in mathematics and computing. And what is the purpose of matrices? Matrices are essential for manipulating and analyzing large volumes of data, essentially enabling complex calculations such as linear algebra, statistical modeling, and system representation. And real world application, that means where do we use matrices? They are used everywhere from Google's PageRank algorithm to physics simulations, representing everything from vast data sets, and also used in financial trading pages. The challenge of information overload. In the age of big data, traditional matrices often become too dense and unwieldy, masking critical patterns and insights. We need tools to manage this complexity. And what are the problems we can see here in the picture? Exponential data growth. The volume, velocity, and variety of data streams overwhelm analytical capacity and increased dimensionality. High dimensionality data leads to curse of dimensionality challenges, making visual and statistical analysis difficult, and signal to noise ratio irrelevant or redundant valuable insights affect decision making. Introducing filter matrices. A conceptual overview. A filter matrix is a dynamic view of a standard matrix where specific rows and columns, that means data points, are selectively removed or highlighted based on predefined criteria. This process focuses analysis on the most relevant subsets of data, leading to faster processing, clearer visualizations, and more actionable conclusions. So here they're given three, that is reduction, focus, and clarity. Reduction brings the matrix to essential elements. Focus directs analytical effort toward high impact data. Clarity removes confusing noise and redundancy. How filtering works, mechanism and algorithms. So here we can see the steps, thresholding, statistical significance, and future selection ML user defined criteria. So let us look deeply here. The filtering process can employ a variety of statistical machine learning and rule-based methods to achieve optimal simplification. Thresholding, how it works here. It's simple rule based on volume magnitude. Example, filter out values below 0.5 or correlations above 0.95. And statistical significance, How it works means only retaining data points that show a statistically relevant relationship or impact. Example, p-value testing and future selection ML using machine learning techniques like random forest or lasso or regressive to identify and keep only the most predictive features or dimensions. And user defined criteria allow the analyst to apply domain expertise filtering based on specific business or research knowledge. And visualizing the filter interactive demands. Seeing the filter in action is crucial for understanding its power. The resulting matrix should be intuitively navigable, and here they give a pre-filter and post-filter. Let us look at the pre-filter, the full picture, a dense correction matrix showing every variable against every other variable, resulting in hundreds of connections and making it difficult to spot outliers or strong groupings. And coming to post filter, focused insights. The same matrix after filtering out corrections below a zero point 0.7 threshold, only the strongest, most significant relation remains clearly revealing clusters and key drivers. Use case 1. Financial portfolio optimization. Identify high risk uh, correlation. That means filtering a covariance matrix to show only asset pairs where extremely high positive correlation. Uh, these assets move together, increasing concentration risk during market downturns, and maximize diversification. Filter to find assets with a very low or negative correlation. These are the optimal candidates for balancing the portfolio and mitigating overall volatility, and strategic rebalancing. The filter matrix provides clear real-time input for algorithmic rebalancing strategies, ensuring the portfolio always meets defined risk parameters. Use case 2. Customer segmentation and targeting. So first, the data will be collected and it is filtered, and the filtered data is made into cluster and it will be analyzed. Then it will be sent to targeted campaign. By filtering cluster attribute, matrices can isolate the most distinctive behavioral and demographic features that define high value segments. Before filtering a matrix of 500 potential customer trains it to sparse and noisy for effective clustering. The filter reduces this to the top 20 predictive traits. Example, purchase frequency, platform engagement, geographical region. And beyond the basis, advanced filtering techniques. For highly specialized analysis, more complex, multi-layered filtering can be applied. So there are three ways. First one is time series filtering, applying dynamic filters that evolve based on temporal factors, showing how relationships, that means matrix values, change over time rather than just a static snapshot. And tensor generalization, extending the concept to multidimensional data arrays or tensors, filtering across not just rows and columns, but also time or other contextual layers. Privacy perceiving filters, implementing differential privacy techniques to filter and aggregate sensitive data points. maintaining utility while protecting individual identities. Benefits and limitations. A balanced perspective, key benefits, improved performance, reduced computational load and faster query times due to work with smaller, denser matrices. Enhanced interpretability. Analysis can immediately focus on the most meaningful data points without distraction from irrelevant information. Better model accuracy. Removing noise and redundant features often leads to more robust and accurate predictive models. And potential limitation risk of bias. Potential defined filters can unintentionally exclude critical outliner data, leading to a biased or incomplete view. And oversimplification, aggressive filtering may strip away subtle yet important weak signals. They are only relevant aggregative. And the final one is initial step up cost. So from the presentation of filter matrices are the result of applying a transformation to a original matrix to remove, modify, or emphasize certain data, leading to specialized conclusions based on the filtering technique used. The primary conclusion is that filtering extracts specific meaningful information from complex datasets, which can significantly improve efficiency, reveal hidden patterns, and enhance the performance of algorithm in various fields. So the key points from filter matrices we got are personalized insights, computational efficiency, targets analysis, and for image and signal processing, future extraction, noise reduction, improved quality. And these are the outcomes we got from the presentation. And thank you.